Good day to all of you. I'm Nicholai Labausa, and I'm going to show you on how to solve series parallel resonance circuits. Okay, before we go on to solve problems, we first familiarize this formulas for the series resonance and the parallel resonance. So in series resonance, the inductive reactance and the capacitive reactance are equal. Resonant frequency is equals to 1 over 2 pi squared of LC, and the total impedance is equals to R, or the value of the resistance. The quality factor is equals to voltage of the inductor or voltage of the capacitor over the total voltage, or it's equal to inductive reactance or inductive capacitive reactance over the R, over the total resistance, or it is equal to 1 over R times square root of L over C, which is equals to tangent theta. So now we will go to parallel resonance. Parallel resonance. In parallel resonance, the inductive susceptance and the capacitive susceptance are equal. The resonant frequency is equals to 1 over 2 pi square root 1 over LC minus R squared over L squared. The total impedance is equal to 1 over total admittance, which is also equals to inductance over resistance times capacitance. And lastly, the quality factor is equals to current of the inductor or current of the capacitor over the total current, and it is also equal to tangent theta. So now we will proceed to solving problems. So this is our problem number 1. A series circuit consisting of a 30 ohm resistor and a 4 millifarad capacitor is connected in parallel with a variable inductor. For what value of inductance will the circuit be resonance if the frequency of the source is 1200 Hz? So we'll go on to our solution. So this is the diagram or the circuit for that problem. So a 30 ohm resistor and a 4 millifarad capacitor is connected in series. So it is connected in series, and the combination is then connected to parallel with the inductor. So the question is, what is the value of the inductor so that the circuit will be resonant? So let me go on to our solution. So solution for this is let me find it. There you are. Solution in series or in parallel in parallel resonance circuits. So the inductive susceptance and the capacitive susceptance are equal. So if we substitute the equivalent for that, it will become 1 over 2 pi 1200 over L, or 1 over XL. So this is the equivalent of the inductive reactance, because the reactance is the reciprocal of the susceptance, or vice versa. Then the next one is the capacitive susceptance. So the equivalent for that is this one. This is the capacitive reactance, and this one is the resistance, and this one is the square of the capacitive reactance. So before we go to that, first we must solve the capacitive reactance. So the capacitive reactance is equal to 1. The formula for that is 1 over 2 pi resonant frequency times the equivalent of the capacitor, or the capacitance. So the capacitance is 4 millifarad, so 4 times 10 to the power negative 3, so that will be in farad. 1 over 2 pi times 1200 times 4 times 10 to the power negative 3. The answer for that is 0.0332 ohms. And then so we will proceed. So 1 over 2 pi, or the equivalent for this is the inductive susceptance, and this one is the capacitive susceptance. So 1 over 2 pi times 1200 hertz times L, or the inductance, is equals to 0.0332 over 3 squared plus quantity 0.0332 squared. Then now we can get the value of the inductance, so that the circuit will be resonant. So let's check. 1 over 2 pi times 1200 times 3.6. The answer for that is let me calculate it. Wait a minute. 1 over 2 pi 1200 times 3.6. So the answer for that is 3.68 684 times wait times 10 to the power of negative 5. Wait. Times 10 to the power of negative 5. Negative 5. So let us check this one. This 0.0332 over 30 squared plus 0.0332 squared. So it's equal. The answer for this one is 3.68 times let's copy this one. Control V. So the answer for this problem is now correct, because the inductive susceptance, this one, and the capacitive susceptance is equal. So let us proceed to another problem. Okay, we're going to the problem number 2. So, problem number 2. A non-inductive resistor R is connected. Is connected in parallel with an inductive reactance of 10 ohms. The combination is then connected in series with a capacitive reactance of 5 ohms. So, 5 ohms. Solve for R at which the power factor of the given circuit would be unity. Unity means the PF equals to 1. So, just draw the circuit. So, the circuit will look like this. So, the reactance of, or the reactance in the, let me go back to the question, of the capacitor, the capacitive reactance. So, the capacitive reactance is 5 ohms. So, since it is capacitive reactance, so negative J5, and the inductive reactance is equals to 10 ohms, so G10, and the value of R is unknown. Value of R is unknown. Then, so we will, the problem wants to find the R at which the power factor of this given circuit would be unity. So let's go to our solution. Solution. There you are. So in finding the total impedance of the parallel branch, so this is the formula. R, or in finding the resistance or impedance of a parallel circuit which have two components, or let's say resistance, the formula is this: resistance 1 times the resistance 2 over the resistance 1 plus resistance 2. So to find the impedance, the total impedance of the parallel branch, so we must multiply the value of the resistance and the inductive reactance. So let us multiply R times J10 over R plus J10, so that we can solve for the value of R. So we must multiply it by its conjugate. So the conjugate of R plus J10 is equals to R minus J10. So the answer for that, or we will come up with the answer J10 R squared minus J squared 100R over R squared plus 100 R times R squared, and J10 times negative J10 is also negative J squared 100, and the sign will be minus, and then negative, and J squared equals to negative 1, negative times negative positive, so positive 100. Then we will split it into two parts. So 100 R over R squared plus 100 plus 100 R squared over R squared plus 100. So there's a J in there. This is the value of the resistance, total resistance in the parallel branch, and this one will be the value of the reactance of the parallel branch. So take note that in our circuit is in series. So to attain resonance in series resonance circuits, the value of the capacitive reactance and the inductive reactance must be equal. So we will use that one to solve for the value of R. So inductive reactance equals to capacitive reactance. So the value of our capacitive reactance is 5. The magnitude is 5. So the value of our inductive reactance in the parallel branch is this one, 10 R squared over R squared plus 100. So I will substitute that in this equation. 10 R squared or R squared over R squared plus 100, or the inductive reactance, is equals to the capacitive reactance, which is 5. So this, we will come up with this one. So cross multiply, 10 R squared equals to 5 R squared plus 500. So transpose this one to this one, so we'll come up with 5 R squared plus 500. So R squared equals to 500 over 5, which will be equal to R squared equals 100. Square root of R squared, square root of 100, and the square root of R, or which is the 100, square root of 100, will be 10. So this is our final answer. The value of R will be 10 ohms. Hi guys, thank you for watching, and if you like the video, please subscribe to my channel. Bye.